Another day, another aspect of this TMAM to discover. Dear viewers, welcome to part 15 in the BUTTMAM series. We are about 3/4 of the way in our explorational journey of this factory, and I think it's safe to say we've reached the summit of this series and can start preparing our descent now. First of all, a small disclaimer. I had to modify the factory between recording the previous episode and this one, because I found some flaws in it. Luckily, firstly, the flaws were not fundamental and could therefore be fixed relatively quickly, and secondly, it regarded the pulsing mechanism of this machine, to which we haven't gotten yet in this series. So, all is good, you as a viewer won't notice those changes. On to today's topic, it is. To quickly sum up the workings of this machine that we've explored so far. The factory extracts floating half layers from the input shape. Those can be duo floats, tri-floats, and quad floats. A set of those candidates will be selected at any one time, and various interdependent filter mechanisms work their magic to try and determine which other candidate pieces are compatible with the ones we're currently considering, and if they're not compatible, they are halted and taken out of the pool. Then, the cross filters take the final shape and extract those quadrants from it that are already contained within the floating pieces that we have selected. And as a result of that process, we could say that the signals or pieces we get for an output, well, they belong to one of two types. Either they are a floating piece, or they are a remainder. The remainder, in that sense, is the group of quadrants that are not contained within any of the selected pieces. It's what we get after having deducted all of the floating piece quadrants from the main input shape. And in practice, that process now translates to the fact that in the bottom right part of the analysis module, a bunch of wires are going to be coming together. To be precise, 16 wires meet each other here. I'm going to zoom out. I'm going to go to the wiring layer. And we are going to have a look at this. You know, this is what I'm talking about. 16 wires come together here. 16 outputs of the other modules join up here. Of these 16 wires, 2 wires may contain quad float candidates. 4 of them may contain tri-floats, of which 2 wires for tri-floats on layers 1, 2, and 3, and 2 wires for tri-floats on layers 2, 3, and 4. Next, 6 of the 16 wires may contain duo floats. Again, 2 wires for layers 1 and 2, 2 wires for duo floats on layers 2 and 3, and another 2 wires for layers 3 and 4. And finally, we have 4 additional wires left for the remainder quadrants, if any, of which 1 wire for each layer of the final shape. Okay? And, well, with this information, with the fact that we have a total of 16 output wires, you can already guess what the next hurdle is, right? We've got 16 wires, some of which may carry signals. We know that not all 16 of them can have signals simultaneously, but we don't know how many actually do, nor which ones. We do know, however, that there are only 4 available tickets, in parentheses, for the grand finale. We only have 4 slots available to which we can assign candidate pieces so that the validator can try to find a solution. The question is, therefore, how can we reduce the amount of wires from 16 to 4 while making sure that we don't accidentally kick out any of the actual valid pieces? And not only that, but also, what order do our pieces need to be sorted in? Because in video 10, I talked to you about how, even though our pieces may consist of more than one layer, there is still a hierarchy among them. the pieces need to be presented to the validator and ultimately the actual physical factory in a certain order so that the final shape can be stacked correctly. And that is what my nester and lane sorter modules are for. And that is what we are going to have a look at today. In a first step, the lane nester is going to reduce the amount of wires from 16 to 10. And it's also going to rearrange the pieces in the correct order, if necessary. And then, in a second step, the reducer module is going to bring the amount of wires down further from 10 to 4. So each step takes 6 lanes out of the equation, and a total of 4 lines will ultimately feed up into the validator. Are you ready? Here we go. So the crossroads is right here. From the left, we are getting 10 lines. To recap, 2 of them may contain quad float pieces. 4 of them may contain tri-float pieces. 6 of them may contain duo float pieces. And then additionally, they meet up with the 4 remainder lanes that come from our final cross filter module. So 1 wire for each lane, for each layer of the shape. So what I initially do, I have 10 wires. And initially, I'm going to pre-sort them in an order that's always going to work out. I'm going to combine the remainders with the duo float pieces onto 10 lanes. This lane carries the remainder for layer 4. These 2 wires carry duo float candidates of layers 3 and 4. This line contains the remainder for layer 3. So we can already see that we have a sorting going on, right? So layers 4, layers 3 and 4, and layer 3 exclusively. Well, you can already guess what these 2 lines are going to contain. These are going to contain candidates for duo floats situated on layers 2 and 3. The next lane contains the remainder for layer 2. These 2 lines contain duo floats for layers 1 and 2. And this line finally contains the remainder for layer 1, if given. So that is the remainder pieces and the duo floats covered. But now it gets interesting. I called this module a nester module. And the reason I call this a nester module is because we are still stuck with our tri-float pieces and our quad float pieces. And the locations we want them to be in, they are not as straightforward as you may think. I'm quickly going to go back to the hub, because if all is well, I have prepared some shapes that will help me with my explanation for today. Come on now, thank you. Let's put that in. We're going to enable the button to turn off auto mode. And we are going to wait until the analyzer module has done its job, finding out how those pieces need to be stacked. Now we can already have a look at the shape. And, you know, I made the coloring so that it's easy to see that this shape consists of 2 tri-float pieces, and they are folded together like, you know, like 90 degrees, like a winding staircase, kind of. Okay, and there we have it. Yeah, let me actually quickly, I'm going to change the coloring so that we can see. I'm going to take red for the first layer. I'm going to take yellow for the second layer. green for the third, and if you've been paying attention in the previous videos, you will know that I will select blue for the fourth layer. There we go. The modules found the pieces, so now we're going to get back to the wiring. With regards to tri-float pieces, we now have them here and here. Okay. And if you remember my color coding, then you will know that red, yellow, green means layers 1, 2, and 3. And yellow, green, and blue means layers 2, 3, and 4. Well, when it comes to tri-floats, my reasoning was this. You cannot stack anything on top of a tri-float that belongs to layers 2, 3, and 4, right? A tri-float piece like this one, it's going to hit the ceiling of what's possible because, you know, there are only 4 possible layers on a shape. So what I am going to try to do is I'm going to try to stack this piece on top of what we already have. And this is for tri-float pieces of layers 2, 3, and 4. On the other hand, tri-float pieces for layers 1, 2, and 3, I'm going to try and stack them from the bottom. So this is why you see this line move upwards, and this other line is moving downwards. And now the reason why I call this module the nestor module is because we have our 10 base lines, our 10 base wires, and these shapes, these tri-float shapes, they are now going to come in from the side, and they are going to try and settle themselves on the first wire they find, so the closest wire they find. In this case, because we don't have anything else on these wires, that actually works from the first try. So, the top line, the first tri-float piece, well, it can nest right here, but if it couldn't, imagine that we have some remainder on the first layer. Well, actually, we will get to that. We will get to that because I have another shape lined up. I remember right now I have another shape lined up that will show that. So the thing it is going to do is it's going to feed these shapes from the side, and it's going to try the first line. And it's essentially it comes down to the fact, you know, it's going to check for vacancy. Is there a signal on that wire already? Okay, then it's going to take the next wire, the second wire. And otherwise, it's going to take the first wire. If the second wire is also taken, it's going to take the third wire. If that's also taken, it's going to take the fourth wire. If that's also taken, it's going to take the fifth wire. Okay? Now, in practice, to be brutally honest, I don't know if I need all of these scenarios. I don't know if there is any practical case in which a tri-float would be forced to take the fifth wire. I don't know. I haven't checked, but I just wanted to make absolutely sure to make this absolutely foolproof, right? I haven't found any problems with this. Let me put it that way. Now, the same thing is going to happen for the other piece, but that is going to try the same thing from the other side. And in this case, because we don't have any of these lines occupied, well, this is also going to be allowed to take the first line. Okay, so now, even though we have two pieces for our entire shape, one of them is on the 10th wire and the other one is on the first wire. We're going to leave it at that for now. Later, we're going to have a look at the other lane sorting module. First, I want to take another shape, and this shape will have a remainder. Yep, there it is. So let's get back. This shape consists of two tri-float pieces and a remainder piece. So, in this case, we see that since we have a remainder piece on the 4th wire, well, here the Nestor module is going to detect that we already have that this line is already taken. So this signal is blocked right here. This shape is not allowed to move onto the 1st wire, and therefore it moves on and it gets to occupy the 2nd wire instead. Why is that? Well, because since this shape, this signal, contains shapes exclusively on layer 4, and this one doesn't contain shapes exclusively on layer 4, quadrants on layer 4, well, this one will need to be stacked below this one. This one will need to be stacked on top of this one. So this is going to be the 4th piece, and this is going to be the 3rd piece. Okay, that's how that works. And if this line were also occupied, well, then it would skip to the 2nd piece or whatever. You know, that's how that works. That's how that works. And it works symmetrically from both sides that way. Okay? Now, that's good and all, but there is another trick. There is another trap to walk into. This mechanism, it only works if your shape has 4 layers. If your shape doesn't have 4 layers, well, I ran into a problem before. Let me pick another shape and show you what I mean. You can see that this shape consists of 2 pieces. It has a trifloat and it has a duofloat. And not only that, but the duofloat needs to be stacked on top of the trifloat. Now, if I repeat my same explanation as I did before, then you're going to see that that shape would fail. Because what happens, well, I get my trifloats and I'm going to try and nest them on the first wires it finds. But the first wire it finds from one side, well, that is going to be the remainder piece of the top layer. And in this case, we don't have that. Okay, so that would mean that the shape would take up this first line. We would get a duofloat below that, so this would be stacked on top of that, and we need the opposite behavior. And this problem arises when we have a shape that doesn't have 4 layers. This one actually only has 3 layers. So the machine needs to be able to cope with that. And let's see how I did that. Well, to be brutally honest, I kind of forgot what it was. Right. Here is my trifloat piece, right? Because of the way the unstacker works, the virtual unstacker, it unstacks from top to bottom, right? If we take some shape, let's say the blueprint shape, it unstacks from top to bottom. So the first output we get is, well, the top layer of the shape. And it is always going to be the top layer of the shape. If we have a shape with 4 layers, then that will be the 4th layer. But if we don't have a shape with 4 layers, if we have a shape with fewer than 4 layers, well, then it's going to be the top layer. So in this case, the 2nd layer. And that, you know, that's a trap to walk into, because that's what's going on here. The way these modules are arranged, these trifloat modules, come on. In the previous explanations I gave, I told you that this cycler would find shapes or trifloats on layers with quadrants on layers 2, 3, and 4, and this one on layers 1, 2, and 3. And that is accurate, but only if the shape has 4 layers. The actual truth is that this module will find the first 3 layers counted from the top, and this one will find the second, the third, and the fourth, counting from the top. But if you have a shape with fewer than 4 layers, right, then this machine doesn't do anything. And that's an easy trap. That's something you could easily forget about that. So that's the same issue that I bumped into. And so I decided that if my shape does not have 4 layers, well then I am not going to nest the tri-float on from the bottom. I'm going to nest the tri-float from the top. And that's what I did here. So I have a tiny little module right here. Actually, we don't need you. I don't know why that's there. But it's going to take the final shape and it's going to see whether there are 4 layers on it. And if the answer is no, then this line will output a null signal. And yeah, those are just there to switch the color of the lines. So a 0 signal or a null signal doesn't really matter. And it's going to cut these lines. It's going to prevent this from feeding onward into the lane nester module from the bottom. And instead, it's going to redirect this line to the top. And it's going to try and nest the shape from the top. And that's what you see happening here. So instead of nesting it from the bottom, it's going to be nested from the top instead. And that is because we don't have 4 layers, we have fewer than 4 layers. Well, more specifically 3, because if we had fewer than 3, well, we wouldn't find any tri-floats, right? So if we have a shape with 3 layers and we find a tri-float for it, then counterintuitively, we're going to need to nest it from the bottom and not from the top. That is for tri-floats. And that is also the hardest part. Quad floats are easier to nest because when it comes to quad floats, it doesn't matter where we nest them. Let's quickly create a shape. There we go. So this shape consists of 1 quad float and 1 tri-float. And the thing is, when we are dealing with quad floats, then any other piece or pieces, they are going to be located on the other half of the quad float. So in this case, the quad float is on top. Well, and the remainder or any other piece, well, it's always going to occupy the bottom. Either the bottom left or the bottom right or both. But this is a situation that always occurs with quad floats. And therefore, it doesn't really matter where we nest the quad float. And in this case, well, I chose to nest the quad float from the top. Right, so that's what happens here as well. Well, and from the top of the module. So in order not to get confused, the top of the module, which means the lower end of the shape lines, the ones that tend to contain the lowest layer quadrants of my shape. Okay, just to make sure that we're on the same page here. Okay, so that's what happens there. And another small side remark I want to make now that I look at it, if I need to redirect one of the tri-floats, I redirect it onto the same wire as the quad floats are going to take. Why? Because it doesn't matter. If we have a tri-float to redirect, well then in 100% of the cases, it's going to be a 3-layer shape, and therefore in 0% of the cases we are going to have a quad float in it. So that means that this line could never lead to any conflict by feeding either redirected tri-floats on it or quad floats on it. There is never going to be any conflict. Okay, I think that's that for the nester module. So we have 4 lanes coming from the top. We have 4 lanes coming from the bottom? Or is it only 3? Darn it, now I'm confusing myself. Yeah, for the first tri-float piece, second tri-float piece, third tri-float piece, fourth tri-float piece, and then to be brutally honest, I don't even remember why I have these additional ones. Yeah, forget about it. The machine works, as I said before. The machine works, and that was the most important part. And as soon as I found out that it worked, I decided not to touch it anymore. I think if I have a closer, quiet look at this, I might remember why I need all of those nester thingies right here. I'm sure they have some purpose, but it doesn't really occur to me at this time. Anyway, what this is going to do, well, we have effectively reduced the amount of lanes from 16 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? And now, at the end of this, we have 10 lines. But more importantly, we have all our pieces in the correct order. This is always going to be the case. After this nester mechanic, the pieces are going to be in the correct order that the validator will need them in. So the only thing we need to do now is remove the empty wires from this. And the way I did that was with this this kind of pyramid module. I don't know what to call this, a lane sorter module. It has like this trickle down effect. Actually, I have a similar module. We already spoke about it. I have one in the fast lane module. This is the exact same principle, except that its layout is a bit different, but it works exactly the same way. So these 10 incoming lines, it's going to reduce that to 4 by letting the pieces fall down until they, bump into a piece that's already there or something. And that way, with each column, let's say, that's going to take off 1 line, and we repeat that until we are left with 4 lines. And then this is going to do the same, but in the opposite direction. So if we have fewer than 4 pieces, it's going to try and sort them as upwards as it can. Again, that's what's going to happen. And then at the very end of this, we have a final little module that is going to make sure that if we don't get an output, well, then this null signal is going to be transformed into a 0 signal. I don't really remember why I did that, but I guess I needed a 0 somewhere along the way. So that's that. And then these lines, now we have 4 pieces in the correct order, and they will move into the validator module. And the validator module, that is something we spoke about before, and therefore that means that by having a look at these wires, you should be in familiar territory already. You should be recognizing the parts that we are looking at. And in that sense, we can wrap it up for today. The nester module is going to sort and arrange all of the potential candidates that I may get. Any range of candidates between 0 and 16 wires maximum. We're never going to have all of the 16 wires, maybe in practice not even half of those, but we can definitely get more than 4 wires, which is why we need to nest these properly, as there may be variety. Sorry about that. Let's rewind. As there may be varieties of lane sorting, lane ordering methods that we need to apply depending on the exact shape and on the exact candidates that we are currently receiving from the other modules. And finally, I need to reduce the amount from 10 to 4 one last time. This is a very easy module, and that's how we get 4 candidates that will feed into the validator. And if we require a 5th layer, well, then that is added right here. And these are the 4 lines that feed into the validator. And that is the end of today's video. Once again, for the 15th time, I hear myself repeating that I hope you had fun watching this video. Thank you very much for doing that. I hope you found it insightful. I hope you find it fun to watch. Whatever, blah, blah, blah. Hope to see you again in part 16. From now on, the topics we're going to cover, they are going to be a lot easier. So I think with this video, with this topic, with the lane nestor and the lane sorter, we have covered pretty much the entirety of the TMAM. You should be having a relatively good idea about how the TMAM operates if you have watched all the previous episodes, all the previous parts. The next parts we're going to talk about, well, we haven't talked about the pulsing mechanism yet, so the way I decide to send pulses through these modules so that the modules know when and how to change, pick a new set of candidates and repeat the cycle. We haven't talked about that yet. We haven't talked about the anti-jank device yet. I wanted to talk about the display stuff, how I operate these displays, but none of those things are really super important to understand the actual way in which this TMAM operates. So with this 15th episode in the series, I think, it's a partial wrap. The rest could be considered to be like bonus material, so thank you very much. If you have any questions, please don't hesitate to note them down in the comments. I'd be more than happy to answer all of them. Or you may reach out to me on the Discord server or through an email or whatever you see fit. So one final time, thank you very much for watching. I hope you are excited to see, the remainder of the videos that I have lined up for you. Hope to see you then and there. Have a great day. I am out. Take care. Bye-bye.